Hello everyone. Within this conference, we are going to present our study titled Performance Evaluation of Interior Shading Systems for Daylight Availability, Glare and Thermal Comfort. Before starting, I want to present the authors of the study. I'm a joint Ph.D. student in architecture. I received my master's degree in interior architecture and environmental design from Yaşar University in Turkey. I'm currently pursuing my Ph.D. studies at Yaşar University in Turkey and the University of Antwerp in Belgium, with a primary research focus on daylighting and energy efficiency. My professor Arzu Cılasun Kunduracı received her Doctorate of Philosophy in Architecture from İzmir Institute of Technology. She has 15 years of academic experience on architectural design and building physics. At present, she is an associate professor in the Department of Architecture in Yaşar University in Turkey. This study consists of 5 parts as follows: introduction, research method, results, discussion, and conclusion. Now let's begin by exploring the first part, the introduction, where we lay the foundation for our research. Daylight availability remains a crucial topic of interest due to its extensive benefits, including improved human health, enhanced psychological well-being, reducing electric lighting loads, thus providing energy saving, aesthetic quality of interiors, user satisfaction, and productivity. However, uncontrolled daylight penetration can lead to discomfort, glare, and visual fatigue, significantly hindering task performance and overall comfort. The rise of glazed high-rise buildings, driven by modern architectural trends, has introduced challenges related to external climate conditions, especially sunlight and temperature fluctuations. As global warming intensifies, these buildings face higher indoor heat levels, increasing cooling demands and impacting energy efficiency. In Mediterranean climates, balancing thermal and visual comfort is particularly challenging due to intense sunlight and seasonal variations. There is no single solution that can simultaneously meet all the diverse requirements for energy efficiency, thermal comfort, and visual comfort. Therefore, it's essential to evaluate the performance of shading systems across various orientations, angles, and positions to understand their impacts comprehensively. This study employs simulation methodology to assess the performance of various internal shading systems, including vertical, horizontal, and roller. In a high-rise building situated in a Mediterranean climate, the primary objective is to determine the optimal shading configuration that maximizes daylighting, thermal comfort, and visual comfort while minimizing glare. The objective of our study is to evaluate how the internal shading types affect the minimization of glare and heat gains while maximizing daylight availability and achieving thermal comfort. In this context, we conducted a case study on the 43rd floor of a glass curtain facade high-rise building in İzmir, Turkey, where the southeast-facing facade provides daylight to the room. A 3D model was created in Rhinoceros, and simulation studies were conducted using Grasshopper with its Ladybug and Honeybee plugins. The thermal and light transmission properties of the materials used in the simulation, like conductivity, density, specific heat, visible transmittance, and etc., were selected to match the actual materials of the building within the Grasshopper library. This figure shows the construction of daylight and thermal comfort models on the software. This table shows the simulation inputs. We placed grid points at a height of 80 cm above the floor and 50 cm from the edges. Then we evaluated the UDI, GA, and TCP metrics using the templates included in the Grasshopper plugins. The evaluated metrics in this study as given in table: useful daylight illuminance UDI, glare autonomy GA, and a thermal comfort metric, thermal comfort percent TCP. The aim was to ensure that UDI remained at a minimum of 50%, GA was maintained close to 100%, and TCP exceeded the results observed in the current environment. This table details the simulation design variables, including the shading elements, fixed properties, in order to thoroughly examine the influence of angles, directions, and coverage areas on thermal comfort and visual comfort in high-rise buildings. 12 shading element configurations were examined. These configurations included 3 angles, 90, 60, and 30, 2 directions, horizontal and vertical, and 2 coverage areas, 100% and 50%. The findings indicate that among the angles tested 30, 60, and 90 degrees, the 90 degrees slash produced the highest useful daylight illuminance values, while the 30 degrees slash yielded the lowest. In 8 of the alternatives, UDI values exceeded 50%, with horizontal slash outperforming vertical ones by 8 to 14%. Additionally, a coverage area of 50% resulted in higher UDI values compared to full coverage, but this also led to a substantial increase in UDI up values, reaching up to 246%. The glare autonomy results demonstrated an increase in glare-free time across all alternatives compared to the base model. In terms of thermal comfort percent, TCP, the results showed higher values for full coverage area compared to 50% coverage area. These are the 3 selected alternatives that give optimal results. Shading elements number 12 provided the highest result for UDI, while number 3 yielded the highest GA, and number 4 gave the highest TCP. In this case, the best values for visual comfort, as evaluated by UDI and GA, were achieved with the use of horizontal 90-degree slats, whereas the TCP result was influenced by the use of vertical 30-degree slats. The base case without shading showed the highest UDI, but also the most frequent exceedance of 3000 lux, leading to potential glare. Simulations show that shading elements can reduce glare without lowering UDI below 50% in most cases. However, interior shading had little impact on TCP values, likely due to the glass facade's low U value and solar heat gain coefficient, which already minimize heat gains. In this case, exterior shading may be more effective for significant changes in TCP values. This study highlights the potential of interior shading in improving visual comfort by controlling daylight and reducing glare. Horizontal 90-degree slats were found to optimize UDI and glare, though results are context-dependent, influenced by glazing type, orientation, and room depth. A tailored approach is necessary for optimal daylighting and visual comfort. While the study shows that interior shading can effectively reduce glare, its impact on thermal comfort was found to be limited. Therefore, we recommend that future research should focus on the integration of exterior shading systems to more comprehensively address both visual and thermal performance in building design. These are the references of our study. Please feel free to contact us if you have any questions. Thank you for your interest.